Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, Panama Buena Vista Union School District, and the Kern High School District. With additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Well, good afternoon and welcome to Do the Math. I'm Michael.
And I'm Scott.
And I'm Colbie. For math homework help, call in Bakersfield 636-4357. Everywhere else, call 1-866-636-6284. Email is dothemath@kern.org. We're online at dothemathonline.net. And on social media, Facebook, Instagram, Twitter, and YouTube.
All right, nicely done, Colby. So go ahead and go like this. Go, whew, that's all done. There you go. All right. So where do you go to school and what grade are you in?
I go to Rio Elementary, and I am in the 5th grade.
5th grade going well so far? Mm-hmm. Good. What kinds of things are you doing in math all this year, like any of the different topics that you've done?
We're working with like subtracting fractions, like bar graphs, whatnot.
Okay, so you're subtracting, you're doing bar graphs, and you're doing whatnot.
That's
Yeah.
right.
All right, well, we're going to do some whatnot today also, all right? But before we get to any of that stuff, are you able to help me out with our social media problem of the day?
Yes.
There you go, that's all I wanted to hear. So let's take a look at the media, or the social media problem of the day on the monitor. All right, so do you have any idea about angles? Have you studied anything about angles yet in class?
Yes, I think we did in 4th grade too.
What do you know about angles? Because it says, what does the angle BOC equal? So it's going from B to O and then down to C. So what can you tell me, when you look at that, what can you tell me right now about it?
That's definitely obtuse, right?
Okay, it is an obtuse angle. And why would you say that? How do you know that?
Because like anything past 90 degrees, which is the right angle, would be obtuse.
Perfect. So what else, what other information did they give us up there that will help us solve this problem?
Well, since there's only one answer past 90, I think it would be 128.
All right, so that's an easy way to think about it, right?
Yeah.
You're like, hey, I know it's an obtuse angle, and I know obtuse angles are past 90. I don't even have to work it out and figure out what the exact answer is because there's only one up there that's past 90.
I like that. Thank you.
So if we had a straight line like AOC, do you know what that angle is?
That is a straight angle.
Perfect,
I
that's a
think.
straight angle. And do you know how many degrees that is?
I think that's 180.
Exactly, so it's 180. So if we know that the whole thing is 180 and they're taking 52 out of it already,
52 minus 180, right?
So you're going to take 52 from 180, right?
So
And
then
that's going to give you
128,
128. So I like how you reason through it
Yes.
though, going, you know
Great
what, it's
reasoning.
obtuse, there's only one answer up there more than 90. Maybe next time they'll put a couple more up there that are a little over 90 and we'll see how they do. But anyway, are you solid on that answer? You want to go with 128, B?
right? Yeah.
All right, let's take a look and see if you are indeed correct. There you go, nicely done. First problem all set. 636-4357 is the phone number. We do have math tutors available most Tuesdays and Wednesdays throughout the regular school year. Time now for today's Math in the News. All right, today's Math in the News has to deal with Tetris. Do you know what Tetris is?
Yeah, it's just like a block dropping game, essentially. is
Yeah,
what
it's a
you could
block
say.
dropping game, right?
Yeah.
Okay. Have you played it before?
Yes.
Do you play it often?
Sometimes.
Do you like beat it? You're like, I dominated this game.
No, not at all.
All right. Well, this was recently in the news. Have you heard about this kid?
Yes, I have.
What did you think of that when you heard that?
I thought it was pretty cool that he was like the first person to do it.
Yeah, it is pretty cool, isn't it? Right. 13-year-old kid, Willis Gibson from Oklahoma, right? He crashed Tetris, right? And it says beating Tetris you have to move the tiles so fast that the game can't keep up with the scoring. So that's what he did. You can see his reaction right there, right? I mean, that's pretty amazing if you think about it,
Yeah,
right?
that
You are
is pretty
faster
cool.
than the game.
You're faster
Right.
than a literal computer.
Right. A 13-year-old kid. I mean, you're in 5th grade, so you got to be, what, 10, 11 years old, something
I'm
like that?
11.
You're 11 years old, right? And you're probably pretty good at playing video games and stuff, right?
Yeah, I'd say so. Certain things.
Okay. Well, let's take a look at the math of Tetris, because we are, after all, doing math today, right? So they're played with tetrominoes, all right? They have 4 squares connected in a variety of different ways. So you can see you can just make a square right here, you can just make it vertical or horizontal, whichever way you align that, but it's basically just pieces of 4 squares put together in different ways. And then, as you said, you're just dropping the blocks, okay? But there's also other math in here because we've got a little bit of geometry in here. So have you, you've obviously done a little bit of work in geometry because you knew about the
Yes.
angles already, right? Have you ever heard of translations, rotations, and reflections in geometry yet?
I do not think
All
so.
right. Well, you know what? With any luck, you're going to in 6th grade, but I'm sure you will in 7th and 8th grade, and definitely when you take geometry in high school. So we have different types of movements, all right? So a translation, you're moving it, and let's go ahead and take a look at an example right here. So you can see that we have the piece up here, the tetromino, and all we're doing is sliding it down, not moving it at all in any direction, just basically just sliding it down like it would drop in the game. All right, so that is a translation,
Okay.
okay? A rotation, so think about if you rotate, you're going around something, right?
Yeah.
So this is going around an axis, right? So you're just turning it, you're rotating it around so that it fits better with what you need. Does that make sense? Okay. And the last one we've got is a reflection. So when you think of reflection, what do you think of?
Like a mirror,
A
or like
mirror.
maybe looking into a
Right,
pond.
a mirror image, right? So that's what it is right here. So it's like looking in the mirror, kind of opposite, right? So those are the different things that are dealing with the math behind Tetris. And you are here on a perfect day. Do you know why?
No.
Well, because you're here, it's the perfect day. But anyway, so instead of tetrominoes, we have pentominoes, all right? So let's take a look at these, and we can see that there are different shapes, okay? But they're all consisted of 5 squares. Do you agree with that?
Yeah.
Okay. And there's a lot of different things that you can make with these different shapes and stuff like that. And a lot of times kids go, oh, you know what? They kind of look like letters, right? So what would this one look like?
That sort of looks like a W.
A W, right? And this one?
I,
An I. What about this one if we draw like that?
T,
A T, right? What about if we,
probably an L.
I know, right? So there's a lot of, there's a lot of things you can look like. Some people go, oh, that's a Y, right? So you kind of get a little creative with the way you look at them sometimes. They're not exactly like that. But what I would like you to do is you're going to have 6 of these,
Okay.
okay? And I'll have 6 of these over here, okay? And I separated them because it's going to make it a little bit easier for us instead of using all 12 at the same time. So what I want you to do, and you can have Scott help you out a little bit, I want you to make a rectangle
Okay.
that measures 5 by 6. Does that make sense to you?
Yeah.
Okay, so if we have 5 right here, how many more can I put along this edge if I had to?
1.
1, right? So I could go like that, and now I have 6, but what does this side have to be now?
That one has to be 5, so that
5.
means you would
So
need
it has to be a 6 by 5, all right? So you have all of these together, and it has to be solid. There can't be any holes anywhere. So I want you to put together a 6 by 5 or a 5 by 6, whichever way you want to do it, all right? So go ahead and start manipulating those around.
I think.
And while you're doing that, I'll go ahead and start on this one, okay?
Okay.
So tell us what you're thinking about and why you're moving things around also.
I think, because when I was first looking at this, I was thinking you could probably make a rectangle out of that.
there
So
you go. Yeah.
if you were to, like, I don't know.
Yeah, so you're well on your way, right? So keep going. See, I've got a square, but I've got this piece sticking out.
Does it have to be? Does it have to be perfectly filled in, or
Has to be
no?
perfectly filled in. So you're doing pretty
Ooh.
well there, but that's open and that's open.
If we were to remove that.
Are there any of them, Colby, that you think might be harder to fit in the hole group than other ones?
Um,
So for instance, this seems to me to be an easy one. You can always just
Yeah.
tack that on the end, right? You can stick it on the end. That's the easier one. Which one do you think is the hardest one to be able to put into your shape?
I think this one, because whenever you use this one, it's kind of like a little.
That
Yeah.
and maybe those, because when I look,
Yeah.
like these are the difficult shapes, I always try to get rid of them.
Right.
Like what I think Scott's trying
So
to
I was thinking, if you can get rid of that first.
get
in
rid of
fact,
the
it'd be great if
difficult.
you could put that one right over there for him, but we got it on our side.
Yeah, I split them
Yep.
because I know which 6 go with which.
There
but
you go.
Okay, I think
So think about trying to get this one maybe in your group,
that's true.
right? And
So
taking up all those little edges and squares, and let's not leave that blank one in the middle there. But that's the tough part, is being able to find a way to make them go together so that there's no extra. There you go, exactly. I like how you did that too. That's a great start right there. So this is going to be the 5 side, right? Remember, and then we're going to go all the way up here for a 6.
then that would be about another.
Ah, there you go.
Here, wait. So then, no, I don't know if that would work or not.
keep going on it
Looking good.
No, I don't think that.
because you've got 5 along the bottom. So
Now,
you
we
only
talked
have
about
6 going up
using
top.
some different parts of geometry as well a little earlier, right? So when you take this shape, maybe you could use it that way instead, right? You could use
That's
it this
true.
way instead. You could use a reflection, or you can do a rotation or a translation. There's all kinds of ways to do that. So just so you know, you can move them around a little bit. If you don't like this little extra piece on the right side, it could be on the left side. Aha.
Probably, I don't think I can. No, I can't do anything with this right now. So then, maybe if I just move that. I don't know. I'm not very good at geometry.
That's
Yeah,
all
you're
right.
right.
It's
I
not,
like the way
it's a
you're doing
game,
this.
right? But
Yeah.
there's a little bit of math behind
Yeah.
it. And because the pieces are all differently shaped, sometimes it gets a little confusing, but that's why we just keep on trying it. Because look at that, you almost got it.
It's so close.
Possibly.
Okay. You're doing pretty good there.
That would not work.
Got a good thought there. Let's try this. We talked about these ones having so many extra edges, right?
Yeah.
Okay. And let's see if we can connect those two in a way where you're going to take out some of those edges, kind of like you had before, right? So maybe something like this. Can you work around that? This would be the bottom side. That'll be the top
So let's
side.
leave these ones
Oh, there you go.
like that.
Oh, okay.
See that. Yeah. So, oh,
Oh, now we're
That's
thinking
okay.
about it.
oops. Oops.
No, you had it. That's a great
There
way
you
to
go.
do it. Oh, and
So
the
you can
tricky
see
one gets
where
in
that
there.
kind of W goes.
Nice.
There you go,
It
nicely
does
done.
work.
So let's go ahead and take a look at it, make sure that we have a 6 by 5. So candle on the bottom, 3, 4, 5, 2, 3, 4, 5, 6, all solid, nicely done. The other one we've got is a 5 by 6. Nice job.
2 for 2.
Look at that. All right, so you ready to do a little more work?
Yes.
Yeah. That's all you have to do is just keep saying yes all the time. And that was today's Math in the News. All right, so we've got Colbie, a 5th grade student from Del Rio. And you said everything's going pretty well at Del Rio, right?
Yeah.
Have you been there for a long time?
I think I've been there since I was in kindergarten, but then I left for a year and then I came back in 1st grade.
Okay. But so you've been there pretty much all of your schooling.
Yeah.
And does that school go to 6th grade, or do you have to go to a different school next year?
It goes to 6th grade and then you move on to Rosedale Middle School.
So that's where you already know you'll be going to Rosedale Middle School?
Yes, most likely.
Most likely. All right. What do you think is the best thing overall about 5th grade?
Well, I mean, there's a lot of good things, so it's kind of hard to choose just
Tell me
one.
one of them.
I bet you they make a wicked chicken sandwich over there. Huh? That's probably a good part of it.
You know, honestly, just like having a lot of good teachers in 5th grade, because this year there's a lot of good teachers in 5th grade at my
Oh,
school.
good. That's an important thing to have at a school. Make sure that you are in favor of your instructors. All right. Why don't you, Scott, head over to the board right now. We're going to get started on a problem. And one thing that I'd like you to do, Colbie, is simply just any way you like, do this division problem for me.
Okay.
All right? 27 divided by 3. How would you do that? I know you could probably do it in your head, but how would you write it out if you had to write it out? So 27 divided by 3.
So there's like 2 ways that I would write it out. 27 divided by 3 or 27 divided by 3.
Good.
But,
Okay, and then how do you go about solving each one of those?
well,
In either way, because you put the order changes depending on how you write it. So that's important to know which one goes where, and the process should be fairly similar, right? Okay, so tell us about how would you go about solving those things?
well, I mean, I think probably if you have your basic multiplication facts memorized, like 1 through 12, then I think it's pretty simple that, 3 times 9 I think is 27, so then it's pretty simple because it's just kind of reversed, so then
Yeah,
almost like that, or just,
there you go. And then you would see from that example that there's no remainder, right? The picture that we had earlier, or the models that we were using earlier, made this big rectangle, right? And the model happened to be 5 by 6. 1, 2, 3, 4, 5. Forgive my not so perfect squares. Okay, so how many squares are in this model here?
so 5 times 6 would be, it would be 30.
30, right? Okay, there's 30 squares. What I'm going to do is I'm going to erase a couple of these pieces here, okay?
Okay.
I'm going to erase over to here, and I took away 3 squares. So how many squares do I have left?
So then you'd have 27 left.
That's it. There's 27 squares. You might be able to see where I'm going with this, right? We're going to see if we can represent this problem with a picture. So here's the 27. The question is, where this 3 part going to come in? What I would like you to do is circle groups of 3. Okay. So in Tetris, there were 4 squares all together, right? In the example that you did here on the counter, there were 5 squares together. And what I want you to do now is circle groups of 3 squares, and we'll see how many groups you have.
So then you would just
There's one, good.
there, and then I would say you could
I like it.
circle
Okay, so we got
like
some different
that.
shapes. Good, that'll work. And then another one, yep. Yep, there's one there. Gotcha. Well done.
And then we just
And
have
then one there. Can you count them up for me real quick?
So
Put a
then-
little number inside each one of them. Just the circles, yeah. 1, good. 2, that's it. Can you guess already how many there's going to be?
7, 9.
Aha. So one way to show this problem in a picture, and it definitely helps younger students because sometimes they don't understand, what does this thing mean? What are you doing here, right? When you first start working with numbers, first start dividing and multiplying, sometimes a picture is a wonderful way to do it. And there's a great picture of exactly what happened. We want to know how many groups of 3 are in 27, right? Or if you had a stamp with 3 boxes on it, how many times could you stamp that right here in this picture here? And you drew those pretty nicely. Kind of like a Tetris game, actually. Kind of works out pretty well.
All
but
fell
that's
right
it.
into place.
Yeah, that's right.
All right, nicely done. Well, Colbie, for your great effort so far this afternoon, you've got yourself a ticket to go see the Bakersfield Condors, so congratulations on that. And do you like the Condors? You like go hockey games?
Yeah, I mean, I sort of understand the rules, so I guess
Okay, well, you know what? I kind of understand the rules too. You don't have to understand all the rules to go and enjoy yourself at the hockey game. So congratulations on that. Right now, we're going to take a look at one of the other manipulatives that you can use in the classroom: 2-color counters.
Okay, well done.
Hi, I'm Cindy, and today I'm going to talk about the 2-colored counters and what you can do with those in math. Okay, so for younger grades, we would probably just start with using 1 color when you're first learning about adding and subtracting. And so for the lower grades, you might be adding, say, 5, so I would put out 5. They would be counting those out. And I want to add on 4 more, so I'm just going to count out 4 more. And now I can see how many I have all together to answer my addition problem, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that would show that 5 plus 4 is 9. You could also use these as a subtraction in lower grades. So if I had a problem like 9, since I already have 9 out there, we'll start with 9. And I want to subtract, let me just mix them up. So there's 9. And I want to subtract 3 from that. I would start with my 9. And I would just take away or remove 3, 1, 2, 3, since I'm subtracting. And what's left would be my answer. So 1, 2, 3, 4, 5, 6. So you can use it for addition and subtraction in the lower grades. You could also use it for multiplication when you're first learning your multiplication facts. If you were doing something like 3 times 2, which really means I have 3 groups of 2. So I would put 2 out, that's one group, and then 2 more is the second group, and then 2 more would be my third group. And so 3 times 2 is 6, 2, 4, 6. For the later grades, or once you start working with negative numbers, which is usually around 6th or 7th grade, you have the 2 colors. So on the flip side of these, there's a red. And how these work is the yellow represents a positive 1, and the red represents a negative 1. Together, it's called a neutral pair or a 0 pair. So the value of positive 1 with negative 1 makes 0, and that's important when you're starting to work with these. Okay, for addition, if I wanted to add positive 3 with negative 6, so I put out 6 red ones. I got my 3 yellows for my 3 positives, and I'm gonna put out 6 reds, 3, 4, 5, 6. What we do is we look at how are we gonna find the answer to positive 3 plus negative 6 by looking at those 0 pairs. So I know that these 2 together, positive 1 and negative 1, make 0. So the value of this is 0. So we can just kind of ignore it. Positive 1 and negative 1, there's another 0. Positive 1 and negative 1, there's another 0. So all of these are 0, but this is what I still have that's not 0. So this is going to represent my answer. I have 3 reds, which means I have negative 3. So the answer to positive 3 plus negative 6 would be negative 3. Okay, now for subtraction, it's a little bit different. You have to start with something. So let's say I want to subtract negative 6. So there's my negative 6. 1, 2, 3, 4, 5, 6. And I want to subtract negative 2. Well, that's going to be easy enough because subtract just means remove. There's negative 6, subtract negative 2. I could do it, no problem. I have negative 4 as my answer, okay? But let's start with that negative 6 again, and instead, let's say we want to subtract a positive from that. So let's do negative 6, subtract positive 2. I have no positives here to subtract that. So what I have to do is consider those 0 pairs. If I put out a 0 pair, I still have negative 6 here and then 0 here. I now have 1 positive counter, but I want to subtract 2. So I got negative 6, I can only subtract 1 right now. So I'm going to need another 0 pair. And now I can see I have negative 6, and then this is 0 and this is 0. So this still has the value of negative 6, but I can now subtract that positive 2 because I now have 2 positive counters that I can remove, and subtraction is removing. So I'm going to do negative 6, subtract my positive 2. I'm going to remove the positive 2. And then you can see what I end up with as my answer, which is negative 6. And then 2 more negatives means I actually have negative 8 altogether. So negative 6 subtract positive 2 is negative 8. Okay. Let's try the same idea with some positives. Let's do positive 2, 4, 6, 8, positive 8. And let's look at subtraction again, because that's the one that sometimes confuses people. If I want to subtract positives, as long as I'm only subtracting up to 8, I have them there to remove. But what if I wanted to subtract 10? Let's do positive 8, subtract positive 10. Well, as you can see, I only have 8. So I could take 8, but I need some more to be able to subtract. So if I put a 0 pair out, I now have 8 positives and a 0. But I see I have that 1 yellow, so now I have 9 positives showing. I need another one so that I can subtract 8, subtract 10. So 8 subtract 10, positive 8 subtract positive 10, I would take off 10 positives. So there's 8, 2, 4, 6, 8. And then there's my other 2, 10. And the answer is going to be what's left, which is this negative 2 here. So that's how you can use these 2 color counters when you're working with addition and subtraction in both the lower grades and the upper grades, where you start learning about negatives, you use the red. When you're just learning about regular subtraction and addition without negatives, you can just use one of the colors.
always fun to find out some of the different manipulatives that you can use in the classroom. Right now, we're going to take a visit with Aamod from NASA. How are you today, Aamod?
I'm doing well. How are you doing today?
I'm excellent myself, thank you. So what is your role or your title with NASA?
So I am the hardware lead simulations group, or electronics engineering at Armstrong, working in the simulations group.
Okay, so simulators, I know a lot of students may be familiar with simulators as far as airplanes go and training pilots and things like that. And you guys do the same thing. So tell us a little bit about how you make a simulator and some of the math that goes into it. And I believe we've got some footage on how you guys are putting together a simulator.
Sure thing. So to build a simulator, what you really start operating is a simulation itself. Simulation is math equation that represent real life. So when you observe the real world and understand how things work, you can take that and then make mathematical equations that now represent the real world, but just in math. So that's what a simulation really is. That's the core of a simulator. The simulator itself is really just a way for a human being to interact with those mathematical equations and do that. So the simulator that you see here, how that itself is built has to do with how do you measure or see when the pilot is moving the switch or moving the knob or the joystick itself. Right? So we just use different ways to capture that, typically using electrical signals, converting it into a digital signal, which then feeds into the computer, which then does all the mathematical crunching to figure out what the airplane in the simulation.
All right, good. So that's kind of how you make it. How long have you been with this section as far as doing the simulators and stuff? How long have you been with this?
I've started in 2018, I believe, in the simulation.
Okay, so I know the next video you've got are the different types of simulators, because it's not always just one type of simulator, because there's some where you could be at a desk doing it, or you would have a bigger monitor or actual life-size things.
Right, so there are a number of different simulations that simulate tours that you can have. So some examples are a training sim or an engineering sim. In our case, we have something we call quality sim. But training sim, as it called, is more for training. So you train the pilots. The cockpit's going to look like the real thing. There's different levels of training. But you're training pilot, or in our case, sometimes we might be training control room engineers, might train any other engineers associated with it. And then we have engineering sim, but really just a simulation to try and understand how the airplane behaves in a variety of.
I was going to say, because you were talking about training and stuff like that, so based on the pilot's level of expertise already, let's say, will also determine the type of simulator that they're going to be using.
Partially. So all of our pilots are test pilots. They're very experienced, but I would say training sim is more for an airplane that doesn't exist. So if we have an airplane that has been flown before, it's good to have a little bit of experience before you go and fly it. So we get the data the best we can, how the airplane would behave using computers, using those mathematical equations, right? And then you put the pilot in there to how the airplane is going to behave if they can, before they actually have to fly it.
Yeah, have them presented with different scenarios so they know how to react when they're actually in that plane. And that brings us to our final segment today, the video that we're going to see right now. This is with the Quest, correct?
Correct, yeah. So this is a simulator of the Quest, or the X-59 aircraft, which is we use for the and yeah. I can talk a little bit about it. The training simulator is the one that we have. This one is different from most of the other simulators that we have in that we built the cockpit to represent the actual airplane. Before the airplane existed, we used engineering to build the cockpit like you would in real life, and then have the pilots sit in there and practice these procedures, normal procedures, and just get them used to what it would be like to fly the airplane, and also start failing some systems, get them practice in flying in not normal conditions.
Yeah, I was going to say, because a plane like that, because even if you're an experienced pilot, there probably has never been an opportunity, as far as I know, where they're going to have to get used to a plane where they can't see the front of it.
Right. There are some analogies in the real world of something that's similar to that, kind of like tail wheel airplanes. You can really see out the front very well. But you're right. For the part, when you're flying an airplane, you have the windshield in the front, you can look out the front. In this case, we don't have. We have a camera, so we have to train the pilot for if that camera fails, and the airplane every time. So we train for that.
Yeah, so if somebody wanted to know a little bit more about this, let's say, I know that a lot of places have internships, and I know that some other people that we've spoken to at NASA have brought up the same thing. But if somebody sounds, they're like, hey, this sounds pretty exciting, something that I might want to look into, how can somebody learn a little bit about some internships that might be available?
Absolutely. So if anybody is interested, I would highly encourage you to intern.nasa.gov. There, we have our interns working on the simulator part of it as well. I've got interns that work for me, so a lot of opportunities within NASA across the country, actually. So strongly encourage anyone not to feel intimidated and apply intern.nasa.gov.
All right, well, Aamod, I certainly do appreciate you taking some time to visit us here today on Do the Math. Exciting things going on always at NASA, and I could just imagine, being in the simulators and then making it so that it's a little bit easier so that when they have to adapt to the actual plane. So, Aamod, thank you for taking some time with us today.
You're welcome. Thank you very much.
All right. 636-4357 is that phone number. We do have phone tutors available on Tuesdays and Wednesdays. We have Colbie, a 5th grade student from Rio Elementary, and loves her instructors at 5th grade, so that's an important thing right there. You've done some excellent work so far today. You were familiar with the kid smashing Tetris, and then you and Scott were able to maneuver those pentominoes in a way to make the 5x6, and then you took that knowledge that you had and applied it to one of your drawings with division. So are you ready to do a little multiplying and dividing at the same time?
Yes.
There you go. See, you can hesitate, but as long as the final answer is yes, that's always the best answer. So head on over to the board. I've got a beautiful problem for the both of you right now. So, do you like cookies?
Yes.
That's it. Everything is a yes, right? All right, so a dozen cookies costs $3.99. So I don't know if you guys want to put up any information right now that might be helpful. So 1 dozen cookies is $3.99.
By the way, Colby, how many's in a dozen?
12.
There you go.
So then.
Baker's dozen for I'm from, Get that extra.
12 cookies.
So 12 at $3.99.
Yep. Good.
Forgot the dollar bill sign.
Good. I'm glad you put the dollar sign on that, because that does make all the difference in the world, because now we know we're referring to money instead of 3.99 miles for 12
Right.
donuts or something like that.
Right.
Okay. So at the same cost per cookie, how many dollars is it going to cost to get 8 cookies? So instead of 12, we only want 8. So we need to know what it's going to cost to get 8 cookies. So discuss it with Scott. How would you like to go about this? You don't have to do anything in your head, but whatever
So over
you're thinking
here,
of, let him know.
the ultimate thing, in using the way that you set this up, we want to know 8 cookies cost how much? That's the goal, right?
Yeah.
So, any ideas about how to approach this problem?
I had ideas and I lost them, and now I'm just confused.
Well, we have 12 in a dozen, right? We got a little box of cookies, and they cost $3.99. Do you have any idea at all how much one of those cookies would cost?
I think you could do division, right?
Why don't we try that, right? Because if you know how much 1 is, then how could you figure out how much 8 is? Like if
We just
1
do-
costs $1.
We do 1 times 8.
That's right. So if you know how much 1 is, we can multiply it back, right?
It's true.
There's other ways to do it as well, but that's one way to do it. Give it a shot.
So I think when you're taking, I learned this, when you're taking money or like decimals or anything like
Yeah.
that, when you're trying to divide it, you
Good.
just
I'm so glad you did it
instead
that way. That's
have
right.
to turn it in to 12 divided by 399.
Gotcha. And you can do it this way too, just by having a little decimal right there, because we really want to know the money part anyway, right?
So that's true, yeah. But then I could just add it.
Either way, we'll have a decimal here or we'll have a decimal there. We can put the decimal in later on. Let's see if we can do a little bit of division, because I know that's your favorite thing to do. So what are you dividing here first? Does 12 go into 3?
Yes, 12 12 can go, no, sorry.
No?
No.
Can't go to that one,
Nope.
right? So
So
that's
we
why
just
you're
gotta
skipping
go
this
over.
spot.
We just gotta
And I'm
go
glad you
over.
put this 3 over top of the 9. 12 goes into 39
Three
times. All right, here we
so
go.
then you would get 12 times 3 is 36, I believe.
Yep, that's it.
So then 36, we subtract that, get 3, and then you bring down
Uh-oh.
your
In
9.
the same spot.
So then we just have to do the same thing over again,
That's it.
and you kind of just,
Well, instead of, so you want to put a
Or this one
36
here.
under there.
There you go.
There you go.
That's all right.
oops.
Good.
So then we just get 3, but I'm pretty sure
Yeah, what would happen
It
at the
just
end here?
keeps
What,
on-
what can you add here on the end and make it keep going?
you can add a 0.
Sure, no problem there. And of course, you could add a bunch of zeros if you wanted to, right? You can have a bunch of zeros, it wouldn't matter. You're going to drop
might-
one at a time?
I might not have
All right, let's give us a
room.
little bit of a room here. I know that you want that to
Yeah.
be able to work out. There you go.
Okay, so then
Now, this isn't 39 anymore. Now it's 30.
this would be 2, I
Okay.
believe, right? Because 2 times 12 is 24.
Mm-hmm.
So then,
And just to help you out, so that you know you're dealing with money, where is the decimal point right now?
the decimal point is right here. I believe.
Okay, and you know that this is going to cost a matter of cents per cookie.
Mm-hmm.
So if you had that information right now, what would one cookie cost if you had to pay for one?
One cookie would just cost.
Because you don't go and go, I'm going to give you 0.332 cents, right?
Yeah.
And keep on going, right? Because it's going to keep on going, right? You're going to
Yeah.
put a 2, add a 0, and it's going to, your decimal's going to keep on going, right?
Mm-hmm.
So if you had that, and I said, I want you to pay me that much money, how much money would you give me?
I'd say about 33 cents.
Good. All right, so 33
Scott,
cents
Don't
for.
let her off that easy. Why is it 33 cents and not 34 cents or something different?
Ah, there you go.
Well,
So you had your decimal here, right?
yeah.
And you just cut it off. You just cut it off to 2 places, which is nice because we only have 2 places in money, which is a good thing. How do you know it's not 34 cents? Or how do you know it's a little bit less? Like where, in other words, the big question is where the heck did that 2 go?
We're,
And what does it matter?
I don't think it really matters. But
Oh,
if
it
you want
matters.
to-
It matters. Numbers always matter in math. It may not end up in your final answer, but it matters, right?
Yeah.
What if this number right here, just for example, okay? What if that number was an 8? It's not, but what if it was? How much would it be per cookie?
It would still be 30. No?
No. What does the 8 do to that 3? You've done some rounding before, right?
Yeah.
Yeah. So the 8 would round it up, wouldn't you agree?
So then you would be 34
It'd be 34
cents.
cents. But we don't have an 8. We have a 2. So that 2, how does that round the 3? Does it make it go down to a 2?
It just stays the same.
It stays the same. So we just need to know that that 2 is important. And it's so important that it allowed the 3 to stay the same, right? So what you found out is that 1 cookie is about 33 cents. Now, instead of having this equal sign, it really isn't exact, right? Because we know the decimal keeps on going. So I'm going to put these little wavy equal signs, and that means about 33 cents.
Okay.
Here's a question for you. How many cookies could you get for $1?
So you could get about 3, I believe.
About 3, right? And that makes sense because $3.99, if you were to round, like we talked about earlier, how many dollars is that if you had to round it?
Well, that would be about $4
About
if you were to round
$4,
it.
right? And what's 4, right? $4 and 12 cookies? About 3 cookies per dollar.
Yeah.
Kind of makes sense, all right? So at least we have an idea what we're shooting for, and we have a good rounding estimate of what the answer should be. So 1's about 33. Now what's the ultimate question we're trying to find out
We're
here?
trying to find out how much 8 cookies would cost.
That's it, you got it. All right, so let's see what you can do with this information. Now remember, we're just approximate, right?
I think if we take
And the approximation will work, but you've got 1 minute to do it.
Okay, let's do it. 0.33
0.33 times 8,
times 8, because you want 8 cookies, good.
and then I feel like this is kind of important.
It's definitely important. All right, let's do some multiplication.
Ugh.
I like it.
Okay, 3 times 8, 24.
Good.
So
Got the
then
4 down there, carrying the 2. And the good thing is you got 24
8 is
again, right? But you're going to have a 2.
again,
Good.
Right. So
Where's the
then-
decimal go? Good job. With the dollar sign?
So then 8 cookies would equal 8 cookies would equal, oh,
Approximately, right?
about,
Yeah, you got your little wavies.
about $2, $2.64.
There you go, nicely
Well
done. I'm
done.
glad you put in that approximately equal to that
Yep.
Scott showed you right there. Put the $sign on that, nicely done. Hey, we do have phone tutors available on Tuesdays and Wednesdays. Right now, we're going to check out Cal Poly San Luis Obispo.
Welcome to Cal Poly, a distinctive, world-renowned university located in San Luis Obispo, California, and founded on one principle: learn by doing. For more than a century, we have proven that the most effective way for students like me to learn and grow is to jump right in, head first, and hands-on. And while we're known nationally for our engineering, agriculture, and architecture programs, learn by doing experiences mean that our students excel in every discipline and every one of our 6 colleges. Mustangs are uniquely positioned with the skills to shape the future of California, and when you help shape California, you change the world. It's one of the reasons we've been named Best in the West for 30 years and most innovative school in the West among public master's universities. It's why this year, we're able to recruit our most academically accomplished, most diverse incoming class ever. From our first days on campus, every student engages in an all-encompassing learn-by-doing culture that you just can't find anywhere else. From co-authoring peer-reviewed, faculty-led research to pursuing passion projects that connect their areas of study to real-world needs. Selena's son chose Cal Poly not just for the computer science program, but for the chance to build something new. Selena founded Slow Hacks to challenge students of all skill levels to use hardware, software, and code to build creative products in one weekend.
I think that hackathons are pretty much an essence of learn by doing. At a hackathon, you spend 12 to 36 hours building a project, which is pretty much what learn by doing is.
Thanks to Selena's leadership, Slow Hacks connects hundreds of students each year and serves as a recruiting event for tech employers.
As for Slow Hacks, I really hope that it remains as a prominent hackathon organization within California and that it's able to positively affect a lot of students around California and around the world.
Real projects with real consequences and real risk of failure. Any Mustang will tell you that is when you earn experience you'll never forget. Zoe Fox was among a team of architecture students who worked with residents of Paradise, California in the wake of the Camp Fire to envision a more resilient community.
This project is learning through service. It's kind of like an emotional investment in your work.
Mustang spent months immersed in resilient design with Professor Stacy White.
Working with a real client is a completely different experience than anything you get from really any other studio. You have to get into the details, like how can this be a real building that can be built and service real people?
On the final trip to Paradise, the teams presented their designs to a community determined to rebuild.
In reflection, I think we're all insanely proud. We've all developed this attachment to the people, to the community, to the project, and finishing is giving them this gift of design, which is the only thing that we can possibly do as architecture students to help this community that's gone through devastation.
Years of learn by doing means that graduates are ready day one to take their future into their own hands, ready to shape their careers, their communities, and California for the better. For NASA astronaut Victor Glover, he took his learn by doing attitude to the International Space Station. While in orbit, he relayed a special message to his fellow graduates.
I want to encourage you to continue to learn by doing. That doesn't stop after you graduate. It sure hasn't for me.
Glover is the latest in a legacy of Cal Poly astronauts. He piloted the SpaceX Crew Dragon and completed 3 spacewalks during his historic mission. Next, Victor could be headed to the moon through NASA's Artemis program.
I want to encourage you to dream big and to be patient and enjoy the journey.
You're now a graduate and member of the Cal Poly Mustang family. Congratulations!
So long for now. Keep shining. Graduates, from up here, your futures look very bright. I expect to see big things from this graduating class. Ride high, Mustangs.
He is one of thousands of Mustangs answering the call, going where California needs them, living a life of learn by doing.
There we go, another one of the great schools in the CSU system. Colbie, a 5th grade student from Del Rio, has been doing some excellent math, and we have a beautiful problem yet again for her. Are you ready?
Yes.
Let's take a look at the camera right now. If you had $1 million and you decided to give away $50 every hour, how long would it take you to give away the total amount? So let's deal with that first before we talk about how old you would be. So you have $1 million and you give away $50 every hour. Discuss with Scott how you'd like to do it, and I have a calculator if you let me know what you'd like to put in.
Okay.
I think you could probably do division with that, right?
So $1 million.
That's a lot.
That's a lot of money. And just like I said in the problem, don't you wish, right? And we want to do $50 every hour. So you just said that maybe it's going to be some division. Tell me about the division part. What are you going to divide into what? In other words, what's the answer you're trying to find first?
I'm trying to find, so it's, how long in hours would it take me to give away all of the $1 million?
Perfect. So you want to know how many hours would it take? Good, that's where the division comes out. All right, what am I going to divide?
So 1
million.
That's hard to write.
Yeah.
Divided by
There you go. Okay, so what do you think? Should we use the calculator on this one?
I say nay.
Got to ask night.
I'm not letting you use the calculator on this. I told you I would, but not on this part. Here's what I want you to do. Cross a 0 off the 50.
Okay.
And cross a 0 off the end of 1 million. Off the end of it.
All of these?
No,
Off
just
the end,
one.
just one.
One for one.
Now, how many times can 5 go into 1?
5.
So Scott, carry on with this.
Okay.
You know where I'm going with it.
Right, we want to go do some division. 5 goes into 1?
They can't go
Doesn't
into
work,
1.
right? 5 goes into 10, how many times?
2 times.
2. Any remainder?
No.
No. So then this one's going to come up, and that one's going to come up, and that one's going to come up, and that one's going to come up.
Okay, so then we can just do this.
Yep, one more. There you go. Good. Where's the comma go?
And right
So what number is that?
So that's 20,000.
20,000 what?
20,000 hours.
Hours. Gotcha. Go ahead and write hours at the end here. So we've gotten to the first part of what you're trying to find out. If you're giving away $50 an hour, $1 million, it would take you 20,000 hours. All right. Now, when you talk about that many hours, we don't usually talk about hours anymore. What would you talk about instead?
Probably in days.
Days. Okay. So now what do you want to do? We have 20,000 hours. How do you make that into days?
So a day is 24 hours.
Okay. So you're going to do division or multiplication?
Division.
Division problem again. All right. Let's see if we can set that up.
So then
This will
20,000.
20,000 hours, and we're dividing that by
24.
This is a great problem for a calculator, I think.
This one I will allow you to do. Right? So this is going to come out to be 833.3.
133. So then.
Okay. Go ahead and write it down on the top.
833.3. So it's 833 and a third days.
0.3. Gotcha.
Now.
And what is
so
this
you know-
again? Right out at the end of it, what is it?
This is in days.
Days. Gotcha.
So it makes it a little easier later on. Instead of 0.3 of a day,
Okay.
figure out what 0.3 of a day is. So you can have 833 days and so many hours.
Gotcha. All right.
So how many, so 1/3 of a day would be how long?
Well, that would just be.
You said there's 24 hours in a day, right?
24 hours
And
in a
what's
day.
24 divided by 3?
24 divided by 3 would be 8, I believe.
8, that's it. So we have, really what we have is 833 days, just like you wrote.
Days and 8 hours.
And we also have 8 hours left over. So far, this is what we have.
Okay.
Now, that's a whole lot of days. So what do you want to change the days into? Because really what the problem asks at the very end is how old would you be? And if you told someone, when they asked you how old you are, well, I'm
have
approximately
to-
21,000
gotta go
days
by-
old.
gotta
They'd
go
be like,
by-
you're kind of a weirdo, right? Usually you tell people you're how old in what?
Years.
Years. We would love to change that to years. How are you going to do that?
So not including leap year, there's 365 days in a year.
Good job. So we got to do some more division, right?
Okay.
Let's set up that division problem.
So then, once again,
833, good. And we're going to divide that by
300 and
3. What did you just tell me?
365.
365, that's it.
That's going to come out to be 2.28, which will become 2.3. Let's make it easy with the decimals and all that. So it's going to be 2.3 years. So instead of saying 0.3 years, how many months would a third of
So
a
if
year
you think about this as 1/3
of a
again, right?
year, so then that would be about 4 months, I think.
Good job. All right, so now we have 2 years and 4
4
months.
and 8 hours?
Oh, and 8 hours. That's right.
So
Right,
that's
that's
how
really
long it would take.
That's how long it would take. So, now Colbie, how old are you?
So
In days. I'm just kidding.
in days.
Right? We don't talk about
calculate-
days. We talk about years usually,
So
right?
I'm-
And then when you're a little baby, you usually talk about some months as well.
So I'm going.
But how old are you currently?
So going by my age.
Yep. What is
So
your current age at the moment?
I'm 11, so then
Okay,
I
so
believe
you got 11.
that would be.
And when is your birthday?
It was just a couple weeks ago. It was February 14th.
So you're really close. That's nice. Okay.
So-
All right. So stick with your 11 on your age, right? 11 years.
11.
And then it's 11. Go ahead and write years at the end there, right? Okay. And we want to put that together with what we have here, right?
Mm-hmm.
And so if you had some columns, you could have a years column, and you could have a months column, and you could have a days column, and you could have an hours column, all that stuff, right? You could have years here, and you could have months here, and maybe you could have
days.
days here, and maybe and the last one you can have H, right? Look, it gets a little messy, but you kind of know what's going on here. So when did you say your birthday was?
February 14th.
February 14th. So how many months has it been extra? No extra months for
0
you, right? How many days has it been since your birthday?
Well, today is the 28th, I believe, right?
Okay.
So then 28 minus 14 would be 14.
14, gotcha. And hours? We probably don't have to worry about that so much. All right, let's put these ones back in this spot here, and we'll see what happens. We got 2 years here, because we know that's going to take that long, right? We also know we got 4 months. So we got 4 months here. We don't have any extra days, but we do have 8 hours.
So while you guys calculate that out, I'm going to let you figure out exactly how old you would be. While you're doing that, in celebration of March Madness going on and the March meets, this week is our friend John, our hot rod expert at the March meets, going to talk about a boost gauge right now, math under pressure.
Hey guys, it's John, and we're back at the Do the Math Hot Rod Garage, where today we're talking about math under pressure, supercharger pressure. For our dragster to go from a standing start to the end of the quarter mile in 7 seconds at over 190 miles an hour, we've got to make about 900 horsepower in our engine. A big component of that horsepower is right here. It's the supercharger. The supercharger is really just a big air pump. This case contains 2 rotors, sort of like fan blades. They're spun by the engine. They draw in air and fuel in the top of the supercharger, compress it against the case, and force it into our engine. That compressed air-fuel mixture is measured in pounds per square inch, or PSI. The supercharger is driven by this cogged belt. This belt wraps around a pulley on the crankshaft and a pulley on the supercharger. This right here is called the idler. Its job is simply to take up the slack in the belt. The teeth on the belt mesh with the teeth on the pulley. That's what drives the entire operation. Our lower pulley is larger than our top in this application. It's got 41 teeth. The top pulley is smaller. It's got 34 teeth. If we do the math on that, we see that the top pulley is actually spinning faster than the lower pulley. Bottom pulley at 41, top pulley at 34. We divide those, and the supercharger is actually turning 1.205 times the speed of the crankshaft. We call that overdriving the supercharger by about 21%. There's one other factor in our supercharger making horsepower, and that's the density of the air that it's pulling into it. And we don't think about air as perhaps having density, but it does. All gases have density. Density is the mass of the gas occupying a certain volume at a specific pressure and temperature. We judge our air or gauge the air with an old school gauge that gives us the air density. This gauge will vary throughout the day. Earlier this morning, it was reading well over 100. The higher the reading, the denser the air. The more oxygen there is in the air to pull into our supercharger. The air is getting thinner as the day is heating up. We'll have to make tuning adjustments on our race car to compensate for that. But that air density gauge doesn't tell us how much boost pressure our engine is making. For that, we rely on this small gauge right here. It's called the boost gauge, and it's a unique gauge. It has a special valve on the back side that allows pressure to come into the gauge but not leak out. That way we can tell the maximum pressure on a run. That's going to be very important for tuning our engine. One of the last things that our crew chief, Billy, will do before we pull the car to the starting line will be to walk up and release the pressure off this gauge. It has a unique pressure gauge button right here on the back that relieves that pressure. We'll take that reading of maximum pressure and record it in our logbook for each run we make down the track. That way we'll understand how our supercharger is working with the air density at a certain reading on our gauge. In our logbook, each run is recorded, and a lot of the parameters of that run are noted. Here we see the blower overdrive, that percentage that we're spinning the blower faster than the engine, and here's the boost that the engine made at that time. That'll all relate to the elapsed time, which is recorded right here, and the mile an hour. By correlating the two, we can begin to get a chart of how our engine's operating at different air densities. And that's another example of math under pressure. This time, supercharger pressure.
Thank you to John for that. We always love math under pressure. Colbie did a little math under pressure, trying to give away $1 million, $50 an hour. How old will you be, Colbie?
I would be 13 years old, 4 months, 14 days, and 8 hours.
All right, nicely done. So it takes a little over 2 years. Come on over here, young lady. So that's pretty cool. You're born on Valentine's Day too, huh? Mm-hmm. All right, so I have a couple of questions for you. Did you learn a little something today?
Yeah, honestly, I would say yeah.
Yeah, probably more than you thought you were going to learn today, right? Mm-hmm. Well, good. That's the most important thing right there. Because when you came in, you were like, yeah, this is the kind of stuff that we're doing in 5th grade. But you've done stuff that you will do in 5th grade, 6th grade, 7th grade, and 8th grade, all today, all combined. So I'm glad you learned a little something. Did you have fun while you were doing it?
Definitely.
All right, good. That's the most important thing also. I'm glad you had some fun. Thanks for coming in, and until we meet again, continue to do the math.
Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, Panama Buena Vista Union School District, and the Kern High School District. With additional production assistance provided by these supporters of education in Kern County and throughout the state of California.